How are you? I'm Paul Cervatka. I'm the Vice President of the Chicago AMS. Victor is not going to be here today. He's got some meetings with some of the big wigs at NIU, so he's like, they're better than we are. Last night, I don't know if anybody saw, Victor and I went on Chicago Night to talk about the upcoming winter weather. And I don't know if you guys have been doing so much at the Weather Service thinking about what the winter is going to be like.
Yeah.
What are you thinking?
All right. Quick summary. It looks active. The bigger question mark is probably where we end up temperature-wise. And so Ricky Castro and Kevin Burke in our office have been looking a lot at past La Niñas in particular and neutrals. Oh, thank you. And so we'll have some stuff on our website probably either next week or the week after. That looks a little bit more in-depth beyond just the equal chances temperature and the favored above normal precipitation part of it. So the big question is the precipitation, if we go above normal, is it going to be rain or snow?
Right.
So, and the other interesting thing, I'll just tease it, is November may be a little bit telling for us for the rest of the winter, actually. So they've done some
We had a
stats
conversation
at that.
about that. I know that right now we're in a, is Ricky going to be here tonight?
Yeah, he sent me.
Yep.
He sent me the PowerPoint a few days ago to look at, which was really good stuff from you guys. So
Okay.
he'll be here. He's coming later.
So we'll have a little chat about it, but
Yeah.
we've got a really good La Nina coming in. It's pretty much there. It's a little subsurface now. It's with the upwelling Kelvin wave, so that the water temperature should be dropping pretty rapidly, and that's. It looks like Victor was talking about the base state of the atmosphere looks La Nina. So finally, the ocean and the atmosphere are back in phase with each other, and that usually sets up to be a fairly active pattern. We've seen it with significant lows that have been traversing the U.S. Interesting thing, we went from this flash drought where we had no rain since I saw Skilling was talking about like 2 inches of rain from August and September. But if you took off the first 3 days of August, we had about a half an inch of rain or less for almost 60 days. And now we ended up the wettest October on record. Second at O'Hare. Well, we still have a few more days left.
13.1 in my
So I just threw up here the 850 temperatures for the next 10, 11 days, and this does not make anybody happy, except for people who like winter, and those people are kind of weird. A lot of winter people. So, and then I guess we're talking about cold in November could lead us into. I'm a little bit concerned about it. So we were.
The gist of it is that colder than average November typically results when you have a La Nina, colder than normal winter for La Nina. And then vice versa, if you have warmer November, then warmer rest of the winter for La Nina years. And if it's somewhere more than average, the signal isn't very good. So
Okay.
to kind of see what shakes out.
All right. Well, great. We can reference this a little bit at the end when Ricky gets here. Maybe he has something to say. Let's move on a little bit more with our meeting. Chicago AMS, do we have any announcements? Anything going on? Still taking membership?
Oh, yeah.
Still taking membership, $20 for the year? Boy, that's a steal. So if we haven't done so, please join us. We are also going to be looking at a November meeting. I think we're planning on a November meeting at Northern Illinois University, which will be a joint appearance with their club. So, and then we'll probably take December off. We've got a couple things on the docket for the end of January or February. And we have a special guest that we're hopefully going to be able to get for the AMS banquet, which we'll do at the end of April. So we have a pretty good busy year, and we'll just continue with this now. COD AMS, do you guys have anything that you want to announce? Amanda, you're here. Anything special for the COD AMS group?
Not at the moment, that I can think of.
Got calendars this year?
Yes, we will have calendars for the Storm Chase trip meeting in December. Oh, I'm loud enough. It's okay. Oh, you're streaming? Okay. Hi, sorry, I kind of just ran in.
Who are you?
I'm sorry?
Who are you?
So I'm Amanda. I am the COD AMS president this year. Just a quick note that we're going to have our calendars for next year at the Storm Chase trip meeting in December.
It's the 8 days after Thanksgiving is our Storm Chase meeting. So if
There you go. 8
anybody
days
wants to
after
go.
Thanksgiving. First Friday in December. So
whatever date that is, 1st or 2nd, something like that.
something like that.
Okay, great. So without further ado, I'd like to introduce Dr. Jason Keeler, who is doing some postdoc work at the University of Nebraska, Lincoln. Jason is quite the mesoscale meteorologist, so he's focusing on a lot of cool issues at relatively small scales. For those of you students who are learning this, mesoscale meteorology. When he went his master's degree, did a lot of stuff on sea breeze, lake breeze, and the influence of the urban heat island on the Chicago lake breeze off of Lake Michigan, which he'll be talking about second. We'll start with your latest doctoral work, which was dealing with wintertime precipitation and some of the convective elements that go on associated with wintertime storms. So it's going to be, what would you call this? A tale
of two seasons.
A tale of two seasons. So we'll get your, boom, there it is, tale of two seasons. So please welcome Jason Keeler.
Thank you, everyone, and thank you, Paul, for the invitation to come out here. So it's good to be back in Illinois. The work that I'll be talking about today is work that I've done over the last 7 years, starting first with my PhD work with Bob Rauber, and then getting into some of my master's work on Chicago's heat island with Dave Kristovich. So I'm going to start off with winter. So this middle section here that was clapping for winter to be coming will be happy with the start of the talk. And we'll be talking about the dynamics of cloud top generating cells in winter cyclones. And I'll get into what those are, but you're seeing some of them right there at the bottom of the screen there. And they're just these little convective cells that you can get at the top of winter cyclones that turn out to have a pretty important impact on the precipitation that you end up getting at the surface. So just to acknowledge the people I've collaborated with on this. This is a collaboration that's been over the last probably 4 or 5 years. So this is with a number of faculty at the University of Illinois, and then also some collaborators out at NCAR who I've been thankful to work with on this. And the few papers that have come from this in the Journal of Atmospheric Sciences over the last couple of years, if you're looking for some light reading after the talk. So I'm going to start off with a visible satellite image of the storm that really needs no introduction in this room. It's the Groundhog Day blizzard of 2011. And so for us weather nerds who were down in Champaign where we were getting sleet while you guys are getting pounded with all the snow, we didn't have the nice snow drifts to look at, but we had these beautiful satellite images to look at down there. And for those of you in this room, you had a slightly different view. And these are just various pictures from around Chicago. And I feel sorry for anyone who was stranded on Lakeshore Drive during that storm. But so all of these images and these different things that we were seeing around the area here with that storm really raised the question, like what causes snow to form, or what causes such heavy snow to form? And so this talk gets into that. And in terms of what we know in some of like the basics of winter storms, so you're looking at this satellite image here, and it's going to throw up what where the low might be in some of your frontal positions. And you typically have that heavy snowfall in that northwest quadrant or comma head or wraparound region, depending on which set of vocabulary is your favorite to use when it comes to winter cyclones. And if we were to look, this is for a different storm, but similar structure to what you might see in terms of the operational radar view of these storms. And so up in northern Wisconsin here, you have these two broad bands of precipitation. So a lot of times you see that banded structure. And we transition to the south there into this more cellular convection. And Paul was asking me earlier, so where do you get lightning in these storms? And it actually is right when you're transitioning from more of that banded precipitation into these actual cells that you get right at the edge of the dry slot is where we found that we get a lot of the lightning in these storms. So if you're Jim Cantore, you want to be somewhere in there. And so let's just take a look in terms of operationally what we would see in terms of some of the vertical structures that you might see. And so if you were to take the 88D data and just take a reconstructed RHI, or just a cross-section through that, you could see that there is some vertical structure here to these bands that were there. And then further to the south, off to the right there, you have some of these elevated cells. And but in terms of research, though, it'd be really useful to see what sort of more of like the fine scale features are in there with data that just aren't feasible to have in real time. And so in the winters of 2009 and 2010, we had a field campaign, the Profiling of Winter Storms, or PLOWS campaign, where we had really an extensive data set where we had aircraft that were flying through the storm. We had the NCAR C-130 that had a suite of microphysical probes, and important for this particular talk, it had a W-band or cloud radar. And so for this particular storm, we flew in this same location. And so this is the structure that you're able to see with a research grade airborne radar for that same time and location. So there really are some incredible structures that are there that are important to what's going on in terms of the precipitation processes in these storms. In terms of structures that jump out, we see that there is this dry slot convection. So we have that dry air that's coming up, and it's sinking and drying there. But you do get some convective cells that actually erupt up into that dry air because there is some CAPE on the order of maybe a few hundred joules per kilogram that you can get in that area. And then we have our deep nimbostratus. So that's kind of that broad wraparound area where you're getting all the more persistent, moderate to heavy snowfall in the cyclone. There's a pretty sharp divide to where that dry air makes it poleward. So just that leading edge there of the dry slot. And then if you look above that area, there's all these almost like fingers of reflectivity sticking up out of that nimbostratus. And so we have these little convective elements that are up there. And if you look carefully, tracing some of these down, you could actually see how the ice crystals that are formed in these convective elements at cloud top actually form fall streaks. And you could trace these streaks of enhanced reflectivity or heavier precipitation from the top of the cloud, in this case almost 10 kilometers above the ground, down to the surface, or to where they merge into these broader bands of precipitation. So those little fingers, or those convective elements at the top of the storm, are generating cells. And that's really going to be the focus of the talk here, is the role that those convective cells at cloud top have in the precipitation of the storm, and under what conditions those convective cells are favored. And so to define a generating cell, the AMS glossary says that a generating cell is a small region of locally high reflectivity at cloud top from which a reflectivity trail characteristic of falling snow particles will originate. And so for those of you who have heard of like the cedar feeder effect, this is essentially you're generating tons of crystals at cloud top that are seeding the cloud below it. So they're just growing as they fall through that cloud. And so these are some images that we have from ice crystals that were observed during the PLOWS campaign. And starting off at higher altitude up top, down towards only 2 to 3 kilometers above the surface down at the bottom. And so these observations that we have in separate analyses that I won't get into too many of the details of tonight show that 80% of the growth of these ice crystals occurs below the generating cell level. And so what you're getting within the generating cell level is that you're just having a large number of very small particles. So they're very aptly named because they are generating all of these ice crystals that will then fall through the rest of the cloud, and they'll grow due to aggregation and deposition, and will become the heavy snowfall that you could get at the surface. And so if we can understand what drives these generating cells, there's a lot that can be learned in terms of what's going on inside winter cyclones at small scales. And so again, this these observations suggest that generating cells are a critical component of those precipitation processes. And so I'm going to be focusing primarily on this one somewhat weaker cyclone and some simulations based on this storm for the remainder of the talk. You might be wondering why I'm focusing on a weaker cyclone. Well, in terms of the climatology of typical lows that will come through the Midwest and produce your snow throughout the winter, the Alberta clippers, like this particular cyclone, are far more frequent than the kind of the real deep Colorado lows that give you the huge storms like the Groundhog Day blizzard. And so your typical winter cyclone is something like this, where you're maybe around 1,008 millibars, and it's an Alberta clipper. So we had some data in plows. We had the C-130 with the radar was flying back and forth over southern Indiana there, and where the red dot is where we had some soundings from the field campaign. And so if I take a look at the reflectivity that we're seeing here, so we're looking from the left is the southwest, to the right is the northeast. And so we have this sharp cutoff in terms of the precipitation. Really didn't have too much in terms of those deep elevated convective cells within the dry slot. So there wasn't any lightning with this particular storm. But it still did produce about 10 inches of snow in southern Indiana. And to give you an idea of what some of the fine-scale structures that we were able to see in these storms, I'm going to zoom in on that area there in the black box. And so really we're able to get some nice high-resolution data showing these individual generating cells there with reflectivities, right around 0. So, it's not a ton of ice in terms of mass, but it's quite a lot of ice in terms of numbers. And on the bottom there, this is our vertical radial velocity, so the particle motion up or down. And so we're seeing that we have some decent updrafts and downdrafts on the order of maybe 2-3 meters per second, with some areas in excess of that. So pretty vigorous convection considering its altitude and that it's in a winter cyclone. So some hypotheses that we're going to be testing here today. First off, generating cells form in potentially unstable layers. So these are layers where the equivalent potential temperature with respect to ice is decreasing with height. So again, it's suggesting that if this layer were to become saturated and were lifted, that you could actually have some CAPE in that layer. And then a more recent hypothesis that long-wave radiative cooling actually will cool the top of the cloud and create some instability that would allow these generating cells to maintain themselves even after any sort of instability that was developed due to more synoptic scale or larger scale processes was exhausted. And so we're going to be doing that using some idealized simulations. So for the people who aren't familiar with kind of more the idealized modeling, these are simulations where the initial conditions in the model are horizontally uniform, and they're just based on a sounding that you provide. And so this sounding is one that I developed based on conditions that were observed in plow cyclones and from a separate, kind of more of a case study simulation of this particular cyclone. For those interested in the technical details, this was a full three-dimensional simulation over a 50 by 50 by 15 kilometer deep grid. We had 100-meter horizontal grid spacing. So this would be what some would call a large eddy simulation, where we really are able to resolve some of the fine-scale convective features, and a fairly high resolution in the vertical as well, 50-meter level spacing. Now you might be thinking, okay, well in these cyclones, that deep nimbostratus that you get, that forms because of processes that occur on the synoptic scale. So you're having this large-scale ascent that you get in response to troughs moving in or to circulations about a front. And if you start out with a horizontally homogeneous domain, you don't have fronts. And so you're not going to have those circulations. And so we actually prescribe the effect of those circulations by changing the temperature and relative humidity tendencies as if you were actually lifting the layer. So we're not actually literally adding to the vertical velocity. We're just changing temperature and humidity based on an input prescribed value of what the large-scale ascent would be in this situation. So it essentially allows the cloud to continue to maintain itself without just deflating over time, which makes for some interesting simulations, but not good science. And on top of this, if everything to this point has been horizontally homogeneous, and the neat thing about idealized modeling is you can get pretty deep into the theory. And so technically, if you have horizontally homogeneous conditions in any model, you could have infinite CAPE. But what parcel is going to go up first? So none, unless there's something wrong with your model. So that's actually another good test. If you don't have some sort of difference in the model and you get convection, there's something wrong with your model. But what we did is we actually added very small perturbations, and by that I mean 0.01 Kelvin perturbations at grid points throughout the model, and very small variations in the water vapor content in the air that were just big enough so that it was technically not horizontally homogeneous. And so this allowed the convection to actually develop. And so enough of the technicalities, onto snow and science. So some key parameters that we are going to be studying here. I talked about stability. And again, I mentioned that we measured this instability based on the profile of equivalent potential temperature. So without getting too caught up in things, I'm going to have simulations with these several profiles. I will tell you which ones are unstable, which ones are neutral, and which ones are stable. But if you do want to follow along for more of the technical side of things, anywhere where you have this profile decreasing with height is going to be a potentially unstable simulation. So A through D are potentially unstable. E, where theta EI is constant with height, is potentially neutral. And then the remaining profiles are all stable. So we're just seeing what kind of convection you could get in storms with a range of stability profiles. Also going to be looking at the impact of radiation. And we're going to have three settings that we're going to look at. One, nighttime, so you're only dealing with long wave radiation or thermal radiation. Daytime, where you have the long wave radiation and the short wave incoming solar radiation, and then no radiation, where we just turn off radiation in the model. So this is going to yield 24 simulations that we'll be looking at for this particular study. And so now to the pretty pictures. And so I'm going to be showing you some plots like this. These are just cross sections through a 10-kilometer long section in the domain. And I'm just going to focus real quick on introducing what these different panels will be showing. So the top one there is the vertical air velocity. So again, you're going to have those warm colors there. You're going to have your updrafts, and the cool colors there, you're having your downdrafts. And for this particular time, we had some nice updrafts, particularly that one on the right there, between 2 and 3 meters per second. Next, we're going to have the relative humidity with respect to ice. And so within that cell where we had that strong updraft, you have some really strong supersaturation with respect to ice. So the relative humidity with respect to ice is well over 100%. And that particular generating cell, it's over 160%. So you're going to have some rapid growth of ice crystals under those conditions. And then I'll be showing the ice mixing ratio. So this is just going into the model's microphysics data and looking at how much snow is there, how much what they call cloud ice particles, and And so just any form of ice within the cloud, just adding up the mass of all of those. And then the last thing that I show in here is what I call the diabatic heating rate. So this is the latent heating as a result of phase change in the cloud, and when appropriate, depending on the simulation, the long wave radiative heating rate and the short wave radiative heating rate. And just for reference, whenever I show plots like this, I'll be showing you in red which stability profile this is. This was for an unstable profile, which makes sense because we have these generating cells. I'm going to be showing some analyses that have more of like the bulk characteristics of these storms. So it's not, unless you guys want to stay here for a few hours, I won't be able to go through the details of all 24 simulations. And so I have a way of just condensing one simulation into one plot. And one way that I've done this is something called a contoured frequency by time display. For those who want more of the technical description of this, what I've done is I've looked at every grid point in the model domain at the altitude where the generating cells were located, so between 6 and 8 kilometers. And I looked at the vertical air velocity for all of those grid points. And the grid points were sorted into bins, 0.1 meter per second bins, based on what their vertical air velocity was. And so for every time that I save data in the simulation, which is every 5 minutes, increasing from left to right, I would color shade them based on how many grid points were in that particular bin. So the non-technical description, and really the thing to take away from each of these figures like this, is to just look at the shape. And so what we're seeing here in terms of the shape is on the left, all of the data are concentrated right at 0. So there's no convection going on at that altitude, at that time. And then we see that that distribution broadens, and that's related to the release of the instability and that convection developing. And then it stays pretty much constant across there. And so that's just showing that we have kind of a steady state where the intensity of the generating cells isn't really increasing or decreasing with time. So we've kind of got this nice machine just chugging along, generating all sorts of ice crystals. But really, just it's the shape that you'll want to focus on for these. And I'll be looking at some time height averaged evolution of the different heating rates and talking about how that plays into destabilization. And I'll be showing you more of those cross sections. So looking now, so we're looking at several of those CFTDs, just looking at how the convection developed in time with the model. And for all of the plots like this, I'm going to show you plots with subpanels A through H. The top 4 are your unstable profiles. This 5th one is the neutral one, and the remaining 3 are the stable profiles. So essentially, as you work your way from upper left to lower right, you're increasing the stability. And so what we see here is as I increase stability, the time at which that convection develops actually gets pushed back. So it takes longer for the convection to develop as you increase the stability. You also see that these distributions up top, they're much broader, so you have stronger updrafts and stronger downdrafts as you in the simulations that start off with more instability, which makes sense. And in the simulations that started out fairly stable, there's a much smaller range in updrafts and downdrafts that you get. But that raises an important point here. So in these simulations, which by the way are for nighttime radiation conditions, you actually develop generating cells. You develop that convection at cloud top, even if the initial conditions were fairly stable. And so we'll get into that in just a second here. And so what you're seeing here, I have color shaded for those same simulations, the long wave heating rate. So this is the cooling that you have at the top of the cloud from the cloud emitting long wave radiation. And so you start out Actually, I should also say that I have superimposed on this those vertical velocity contours. So you could have some idea of how the cooling here relates to the development of that convection. So we start out, though, with a fairly broad, deep layer of weaker cooling early on in these simulations, focusing on panel D there. But so that cooling is going to destabilize the cloud top and allow that convection to develop. And when that does happen, you get this an increase in the maximum magnitude of that cooling, but it's occurring over a much shallower layer than before. So there's this transition from destabilizing the cloud top from this broad, deep cooling to when the convection develops, it really focuses and you have a much more defined top to the cloud. So that cooling is really focused in a shallower layer. And one thing that I found interesting, so I have the maximum cooling rate. This is in Kelvin per hour. And you have stronger cooling in the simulations that started out with more instability. So it almost seems as though if you have more instability because of what's going on the synoptic scale, that these generating cells will develop, they'll be more vigorous, and they're actually going to really focus that cooling at cloud top. And so essentially, strong instability favors maintenance of strong instability, at least in terms of the radiative effects. So if I switch over to now looking at those same stability profiles, but for daytime simulations, the only thing that's different here is that we've included shortwave radiation, so solar radiation. And so now there's something that could actually act to offset that cooling. Not completely, it doesn't cancel it out, but it does offset it to some extent. And so what you get are these simulations where you get this big blossoming of convection. And in that earlier point in the simulation, your vertical velocities aren't that different. But that steady state, when that distribution is a little bit narrower there later on in the simulation, there is weaker convection. So essentially what you're seeing here is that there's this release of instability that was pre-existent, but it almost suggests that it does suggest that when you have daytime conditions, that solar radiation is actually going to limit how strong the convection can get at the top of the cyclone. And this does actually decrease the amount of ice that's produced as well.
Jason, you're saying
Yeah.
that the solar heating is going on at the top of the cloud.
Yep, so it's the same thing. Everything's going on at the top. And so I'm going to show in the next couple slides how those two things are occurring at the same layer. So let's see. Pretty much said all that here. And so even in the daytime, you still do get this convection to develop in the stable cases, even though you have that offsetting of the destabilization. And so looking at how the long wave cooling compares to before, it's maybe a little bit less focused later on because you end up having weaker convection. But if you focus on where that cooling is occurring, and I now show where the heating is occurring, it's that same layer. It's the top of the cloud is what's going to be able to emit long wave radiation into clear air without more cloud just re-emitting the radiation and having it go back down. So if I were to have like a cirrus layer on top of this, it would actually help to cancel that out, because the cirrus layer would then emit some long wave radiation that would go down. So it being the top of the entire storm essentially is able to emit that long wave radiation, but it's also the first layer of cloud that's going to be absorbing the incoming solar radiation. So it's all happening in the top couple kilometers of the troposphere. And again, here we're seeing that when the convection is weaker, there's less heating in this later time there. So in terms of what happens when there's no radiation, we see that the generating cells or the convection only develops when I start off with instability. So in those first 4 panels there. And if I look at panels F through H, there's essentially no range in that. It's more or less just everything concentrated right on that line. So that's saying if there's stable conditions to begin with, that and you're not including the effects of radiation, you're just not going to get the generating cells. That really does drive home how important the long wave cooling is, and how important something like radiation is to a winter cyclone. And we see here in this one neutral simulation that there is some convection that starts to develop later on, and that's actually more of a numerical, it's an artifact of the methodology used in the simulation. But if I do remove any wind shear from the simulation, you don't get that convection. So I'm just developing, it's essentially an artifact of the way that the effects of large-scale ascent is prescribed. If anyone wants to get into the technical details of that, I'd be happy to get into that a bit more in the questions. So just taking a quick look at what's going on early on in the simulations. This is one of the unstable profiles there, 80 minutes into the simulation. And so we see that we have convective cells that do develop when there is that initial instability, regardless of whether it's nighttime, daytime, or no radiation. Because again, I'm providing instability that would be there on the synoptic scale anyway in this particular condition. And so we have some really strong vertical velocities. And so this is actually the same panel that I was showing before, where we have strong updrafts, RH ice greater than 165%. And since we're at pretty cold temperatures, we're at about minus 50 Celsius at this particular level. So you put a 3 meter per second updraft at a temperature like that, and you're going to produce some ice pretty quickly. And then not surprisingly, because of all of that ice that we're developing, we're putting off quite a bit of latent heat there. So you have this strong heating within the generating cells, and you can see the cooling that's there at cloud top because of the long wave radiation. And again, of the 3, so it's nighttime on left, daytime in the middle, and no radiation on the right. We could see that there's this strong cooling, weak cooling, and you don't see the cooling when there's no radiation. And also underneath these generating cells, if you look at the ice mixing ratio there, you see these nice little fall streaks. That's just all the ice that's been produced in that cell falling out, where it's going to then grow and become this heavy snowfall that you could get at the surface in these cyclones. If I look at a later time, so this is an hour later, we see that we still have this convection going on at nighttime. It's weaker during the day, and it's really started to fall apart if we take away, if there is no radiation in the simulation. So it's essentially showing how, in the absence of radiative forcing, once you use up that instability that was there in the initial conditions, that's all you're going to get. And so absent any sort of differential advection, say warm air advection with cold air advection above it that you could get in the cyclone, absent something like that on the synoptic scale, you really are relying on radiation to keep things going in the cyclone, at least in terms of ice production. And so again, we could see here this nice generating cell with similar characteristics to what I talked about earlier. And again, the cooling continues to be most pronounced in that nighttime simulation. And we maintain those fall streaks there in the ice mixing ratio. So now let's look at the most stable simulation. So this is the thing that was surprising to me and surprising to a lot of people that I worked with on this project. We thought, okay, let's just, let's keep on increasing the stability until we just don't get generating cells. Let's show how we turn off this convection in the winter storms. And this was a fairly stable profile that we had here. And we started out, this is 80 minutes into the simulation, where in terms of the vertical velocities, you've got nothing. There's not any sort of convection. You do have some supersaturation with respect to ice. I mean, the cloud's there, it's ready to go, it's just not convecting. And again, we have this broad cooling at cloud top in the nighttime simulations and some weaker cooling in the daytime simulations. So it's destabilizing. So this is going to gradually tilt that profile back to a point where you can get convection. So moving on 1 hour later, without radiation, you're not developing the generating cells. The daytime radiation, we're starting to form some cells at this point into the simulation, but they are pretty weak at this point. And then with nighttime radiation, where you're going to really maximize your destabilization because you have cooling at cloud top that's not being offset by solar radiation, you're going to develop some pretty well-defined generating cells. So to summarize the winter storm portion of things here, we have these generating cells that are fairly important in the precipitation process in winter cyclones. I mean, they are the initial production of ice crystals that'll then grow in the rest of the cloud. So these generating cells are going to develop in the presence of cloud top potential instability that, say, is there because of what's going on the synoptic scale. But they're only going to persist when radiative forcing is present. And under neutral and even stable cloud top conditions, radiative forcing is going to destabilize the cloud top to the point where generating cells develop. And to me, I'm excited about this result because in all of these different field campaigns that we've seen in recent years, we see generating cells at cloud top all the time. And so this provides a physical explanation of why we keep on seeing these generating cells in winter storms. And another interesting point is that the generating cells are going to consist of stronger updrafts and higher ice precipitation mixing ratios at night when destabilization due to long wave cooling is not offset by shortwave heating. And this raises a question that I'm not sure how to answer yet, but I want to answer, and I'm looking for ways to do this. If these generating cells are producing more ice at night, and that ice gets to go through the rest of the cloud and grow, this suggests that winter storms might actually produce more precipitation at night. All else constant, you might actually get more snow if a storm comes through at night than during the day. I'm not comfortable making that a conclusion yet, but it's something that's worth looking into. And one other final point on this is that generating cells don't develop in the absence of radiative forcing unless cloud top potential instability is there because of what's going on larger scale. And in the case when that large instability is there at the beginning, it's going to just get used up and the generating cells will fall apart without radiative forcing. So that's what I have for the first part of the talk here. I don't know, Paul, should we just do all questions at the end? Okay, so how are we doing on time?
7:45, about 15.
Okay, sure, great. And so this part, this was fun for me to put together. The work that I did on the influence of Chicago's heat island on Lake Michigan lake breezes is some work that I did at this point almost 10 years ago. So this is really one of the first projects that I dove into as a grad student down in Champaign. And so it's nice to actually think about some stuff that I did a while back, especially since it's relevant to a lot of people in this room. So do want to acknowledge my collaborators in this project, my former master's advisor, Dave Kristovich, down at the Illinois State Water Survey, and we had some of the former boundary layer meteorology group members here, and they're spread all over the country now, ranging from NOAA to, I believe, the Air Force. Faye is actually a forecaster at the Upton office. dealing with lots of nice coastal meteorology. So I just want to start by looking at these pictures. The top two are from, obviously, here, and the bottom one is from closer to where I grew up in the New York suburbs. And so you look at those, there really are some stark differences that you have, and especially with Chicago being, the extremely built-up portion of Chicago being right on the lake shore. There really are some drastic gradients in different kinds of like surface characteristics that we have here. So it's a place where neat weather should happen, and it does, because of these really stark contrasting water next to city, smooth surface versus very rough surface. And so some neat things that can happen on the mesoscale because of that sort of orientation. And just to think a bit about the lake breeze circulation and the heat island circulation and how these things might interact, I just wanted to use these pictures as examples. So the heat island itself is it's due to the thermal characteristics that you have within the city, where you do tend to have higher temperatures in the city, which is going to lead to a lower pressure, and you're going to get this nice circulation with the convergence at low levels rising and then divergence above that. And so you might see something like that in terms of some sort of circulation, potentially at differing scales. And then with this being right at the lake shore, if there was a lake breeze going on, you'd have that cool air going into the board there. Looking at things from the side there in that middle panel, if I were to have the sea breeze circulation there, again, that cooler, more dense air spreading out over the land, you might have this circulation coming in like that. But you're also going to have the heat island circulation, which will be right next to that. And so you could get some pretty interesting interaction between the two. And so in this little slice here, you're going to have the circulation going like that, but this is a 3D circulation. So standing here, if you had a pretty strong circulation due to the heat island, you'd have wind at your back. And then on the other side, on the south side of town, you'd have wind coming the other way towards the center of the city. And just to think about how you could get all sorts of different orientations in terms of these fronts and different ways that these circulations can interact with each other. This picture on the bottom is actually of the Long Island Sound viewed from the mainland. So you're on the mainland, but that little strip of land that you see off in the distance is Long Island. And so you're actually seeing there a situation where you still have this warm air that's going offshore, off of the mainland, but you have that, in that case, a sea breeze front. So that's the Atlantic Ocean sea breeze coming up and over Long Island and then maybe crossing over the Sound towards the mainland. So I just want to show these just as ideas of all different types of circulations that you could have in these particular areas. And so these are problems that are really kind of classic mesoscale meteorology things to look at. And just in the interest of time here, I'll skip ahead, but know that we do have just an example there from St. Louis, where you have this convergence on the center of the city. And just showing an example of looking at, in terms of sea breezes or lake breezes, the types of variability that you could get from these fronts. I have a couple images there. The one on the left is from some of my own analysis, where I just show the hourly position of the lake breeze front, as in July of 2005, a case that I looked at. And you see all these neat little squiggles in the front there. And that's actually the lake breeze front interacting with horizontal convective rolls. And so this is a day when you had winds there from the southwest, I believe, and so you had all these nice little convective rolls that were just kept on intersecting the lake breeze front, and you had all these nice little wiggles in the front there. And that could actually have some pretty important implications if you want to look at, is there a spot along the lake breeze that's going to favor a thunderstorm developing, when you might, get enhanced convergence when you have a convective roll going into it. So that's something in future work that I might want to take a little bit more of a look at. Some key things that previous studies have shown in terms of sea breeze or lake breeze interaction with heat islands is that the lake breeze could actually displace the heat island. So in this case, in downtown Toronto, you've got Lake Ontario off to the south there, and this contour there is your warmest temperature. And so the lake breeze coming up off the lake is actually just displacing the heat island further inland. So that's one thing that you could get. Some other and these are modeling studies now, have shown that you actually get a rapid inland motion to the center of the city. So in that picture that I was showing before, where you're looking down at Navy Pier from the north, you'd have that one part where the airflow of the sea breeze is in the same direction as the airflow due to the heat island circulation, so they're additive. And so you would accelerate into the center of the city, but then all of a sudden, as you try to move into the inland suburbs, where we are right now, you're going to have an opposing flow. And so this was all done in simulations. And so really the main focus of this study that I did was to say, okay, does this actually happen? Or more importantly, does it happen in Chicago? And can we observe that with standard atmospheric data? And so I'm actually going to skip ahead a little bit to that. This is the climatology of heat islands in the Chicago area from Ackerman, 1985, just showing that you have your, so you have the time of day there and the year of the month. So you're going to have your strongest heat islands overnight and in the summer around here. So yeah, it's just more of the question here that we're going to be looking at moving forward is, do they actually move more slowly through the suburbs? And so first we need to identify enough cases with lake breezes to do this analysis. And so I kind of dating when this study happened, but I was looking at cases from 2005. And so there was the first kind of step in eliminating dates. So I looked at days April through September 2005. Any day that was completely overcast in the area was eliminated, and any day that had obvious lake effect precipitation going on was eliminated. Because again, your sea breezes or lake breezes would be favored on the warmer days. And also then looked at the 0.5 degree reflectivity data from Romeoville for all other days. So you could tell this was some of my earlier work because I did this the painful way, and I manually looked at approximately 15,000 radar images that summer. The benefit of that is I could pick out a fine line very easily now. Might be burned into my retina somewhere. But so once we had those dates, I looked at the surface data, and we wanted to look for a couple things. We wanted to make sure that there was convergence along the fine line. So in that case, it was right through there where we had our convergence. And we wanted to make sure that we had cooler temperatures lakeward of the fine line. And so if you look at these couple stations here, we could see that we're in the low 80s as opposed to the upper 80s or even 90 in some cases further inland. And so we ended up with 49 dates with lake breezes in the April through September 2005 period. And we eliminated 5 dates because there was enough convection that was going on that it was hard to tell whether you're really looking at an outflow boundary or the lake breeze. And we really wanted to focus in on lake breezes for this study. Can go into this in a bit more detail later on, but essentially the number of lake breezes that we had this year and their distribution throughout the year was consistent with earlier climatology. So we feel confident making statements that this is a representative year to look at. So just an example of some of the differential movement we could see here. So we're looking at this one case, and this is at one earlier time in the day where the position of the lake breeze front is pretty much, it matches the shoreline shape, which is kind of a classic thing with lake or sea breeze, is that absent any other sort of forcing, you would essentially have a front that mirrors the shape of the shoreline.
Do you know what time of the day that
I'd have to go back and check for this particular case. Chances are it was late morning and then a few hours later. I do have some data that I could dig up in terms of when the fine lines were first visible and when they ended. But I don't have that within the PowerPoint just now. But we could see that at this time later on in the day, there's been much less progression inland near the core of Chicago, whereas to the north and south of the city, it's made it in much further. So great, we found one case. But in terms of a broad statistical sense, if we wanted to look at all of the days and we want to correlate them with the strength of the heat island, we really need to have, that'll give us some more confidence in the result. So I looked at the hourly position of the lake breeze front along several shore perpendicular cross sections, and I was able to calculate the inland motion of the lake breeze front along each of those cross sections for all hours during all of the 45 cases. And so we've compiled this data set of the hourly inland motion of the lake breeze front along each of those cross sections, but we want to correlate that to the urban heat island magnitude. And for some reference points, I did that when the lake breeze front crossed 3 positions in the Chicago area. The red dot midway, I looked at the intersection of 55 with 294 and the intersection of 55 with 355. So kind of these 3 points where we wanted to see how the lake breeze front was acting across all of the cross sections when the fine line crossed over those points. And kind of the thing that jumped out, so I have some correlations here in the number, and the significance is shaded for when it crossed midway, 294 and 355. And again, these sections that really go through the city and the suburbs are 4, 5, and 6 there. And so if I look at the UHID, so that's the daytime temperature difference between Midway and Aurora, which I used to define the strength of the heat island. And I looked at that right before the lake breeze first formed. And there wasn't a statistically significant relationship with that. However, if I look at the maximum nighttime magnitude of the heat island for the early morning preceding the lake breeze, we find that by the time the lake breeze front gets to 355 on the right there, there's actually, in cross sections 4 through 6, a statistically significant negative correlation. So we found that as the lake breeze front moves through these more inland portions of the suburbs, we do find that on days with stronger heat islands, you do have slower lake breeze frontal movement through where we are here, essentially. We're kind of right in the prime area for Chicago affecting the sea breeze. So if you happen to live right around here and you ever have a really hot day and you just wish that the lake breeze would come in, sorry, the city is probably preventing you from cooling off. So in general, this correlation and significance will increase further inland, and we weren't able to find an effect near Midway, and it's quite possible that's just close to where the center of the heat island circulation is, and so you're not really going to have a clear positive or negative relationship. And I think with that, I've already gone through these points, so I'd be happy to take any questions, and thank you for your invitation and attention.
Okay, so we've got time for a couple questions. I know we're going to have a couple of microphones come around, so just raise your hand. Marianne, maybe down here. Over here in the second row here. Raise your hand, Marianne. There she is.
Hi.
Hi.
It's nice to meet you. I was made aware of your study in 2007.
Okay.
And it was why is Dupage so hot compared to the rest? And it was from the heat island effect moving inland from the city, and the city getting more cooling. So in the winter, the winds, don't they change direction? And it does stay warmer in the city because of the lake, but is there a limit to how warm the lake keeps Chicago?
So in the winter?
Yeah, so when on the flip side,
Yeah.
you know, going the other way, I mean, in the summer, we're hotter than we normally would be because of Chicago.
Yeah.
In the winter time, we're 5 degrees colder on average than downtown Chicago.
Right.
But what is the downward temperature limit, and how does it affect the difference?
Yeah, and so that's something that I haven't investigated. But you do raise an interesting point, though, that you know, in the winter, you'll have your coldest days here when the winds are either calm or offshore. I mean, if you're getting onshore flow, the lake will definitely warm you up out here. But if you have a heat island, that's going to make sure that your winds are even more offshore out here. So it is possible that there could be certain conditions where the heat island might actually keep you cooler if it's extending further east. Yeah.
Thank you.
Yeah, here, just so you can see, here's your heat island.
Yeah.
In the cold season, you have
It's
a lot less than in the summer.
yeah, it's less pronounced in the winter in terms of the climatology.
Yes.
Okay. You mentioned that there was sometimes cirrus layer above the cyclonic position itself.
Yeah.
Now, back just a few years ago at the European Center for Nuclear Research, it was strongly suggested in an experiment they called CLOUD that cosmic rays might increase the amount of that type of cloudiness. And right now, the amount of cosmic rays is going up because of solar magnetic activity going down. Is anyone making any studies right now as to whether that's going to maybe then increase the intensity of these snowstorms?
So yeah, I'm not aware of any studies that have gotten into that, but if you were to have a situation where there was a cirrus layer above the, there's a deeper cloud layer, a gap, and then a cirrus layer, that would actually prevent some of that long wave radiation from really escaping to space. And so it would be absorbed by that cirrus layer, but then re-emitted, and so some of that would go back down. And
you were mentioning that it would go downward, and it almost seems counterintuitive for a long wave.
Well, but I mean, long wave, it'll
be
emit
going upward rather than downward.
Well, it emits equally in all directions.
Yeah, okay.
And so it's just that some of it will go up and some of it will go down. But it's just by having a separate cloud layer above the deeper cyclone, that's something that could happen, where that could actually affect the ability of the cloud to
You'll actually
maintain,
see, just in simple explanation of that, you'll see that in the evening time, when we're looking at cold temperatures and record temperatures trying to get down, once that cirrus layer comes up, the temperatures don't just stop going down, they actually come back up. So when it's clear throughout the atmosphere, you're going to see that effect with the cirrus layer, that your temperature is actually going to increase at the surface.
Yeah, and then there was actually, I think there was a study that looked at the effect of aircraft being grounded after 9/11, and showed that in that week or so after the fact, when there was a lot less commercial aircraft, that there was even an effect in terms of the temperature just by not having contrails.
For the extent of the lake breeze, did you consider friction? Because I understand the concept with the potential heat island impact, but also where the heat island impact would be the greatest would also be where the friction would be the greatest, most likely. So that could also be part of the limiting factor as far as the inland extent.
Yeah, and that certainly could, but we did have days where I think there were at least two of the days that summer where the lake breeze front made it into Rockford. So it can make it in pretty far. And I think that the nice thing about this study, well, at least from our perspective, we were really trying to isolate the effect of the heat island, the temperature difference in the circulation, as opposed to the friction, which had been the focus of a lot of earlier studies. But the friction is really not going to be changing day to day. And so, but the heat island will. And so that's why we really liked kind of isolating, looking at just the temperature difference and the speed of the front.
Yeah, thanks. Anyway, I can attest to that going out to Rockford because I live in northwest Boone County, which is just 13 miles from Rockford, and I have felt them come out that far.
Yeah.
And I've seen them on the radar displays, that
Yeah.
they do actually go out that far.
And it especially helps if you have days when there's a larger scale cold front coming down from the northwest. It almost seems like it helps accelerate the lake breeze front inland. I think the day when we had it go furthest inland was the day before a cold front came through the Midwest.
Time for one or two more questions? Anything else? Okay, if you do have any more questions, then come talk to Jason afterward. Thank you very much for coming here today, and we'll let you know about the November meeting as soon as Victor gets that on the schedule. So thanks very much, guys.
Thank you.